Hi everyone. Sorry for the delay. Welcome to the second Eurographics Star session. First of all, let me introduce myself. My name is Andreas, and I will be the chair for this session. The session contains only one state-of-the-art report, which is entitled by a survey of multifragment rendering. And this is a joint work by myself and Kostas Vardis and George Papaioannou, all from the Department of Informatics at the Athens University of Economics and Business in Greece. And the presentation is pre-recorded and its length is about 47 minutes. So you're going to have plenty of time in order to ask questions through the Discord chat channel and the YouTube chat channel respectively. So let's move to the action.
Hello, and welcome to the presentation of our survey paper with title A Survey of Multifragment Rendering. My name is Kostas, I'm the person in the middle, and I'm a postdoctoral researcher of computer graphics at the Athens University of Economics and Business in Greece. So, multifragment rendering is a family of rasterization-based image synthesis techniques that is responsible for the delivery of various complex visual phenomena in interactive and real-time rendering. The main advantage in these approaches is that they're able to store, compute, and process information that resides in the hidden layers by essentially augmenting the traditional primary visibility determination states. And with this survey, we provide an overview and insight into this exciting field of research. The presentation is split into three main parts. In the first part, we will define and present the multifragment rendering pipeline, or MFR, and also clarify what this star actually focuses on. Then we will proceed to generalize MFR as a general visibility determination problem, and in there we will also define a conceptual rendering pipeline for it. In the second part, we will elaborate and discuss this pipeline, and we will start by detailing construction strategies for the various MFR data structures, the core operations that can be performed on them, and finally their mapping to the respective applications. And in the last part of the presentation, we will discuss some existing and hopefully exciting open problems and challenges, and conclude by presenting opportunities for future research directions. So, multifragment rendering describes the methods and algorithms, data structures that are used to produce, maintain, and process sets of geometry fragments that first correspond to the same location in image space, and second, they are captured from the same viewpoint. Therefore, it does not describe methods that process information from multiple viewpoints, and second, it does not describe data structures that are addressable in object space, like voxelization techniques. And also, multifragment rendering has been described with various other names in the literature, such as deep G buffers, layered fragment buffer, and others. And in this survey, we decided to avoid complicating matters further and use the term MFR and multifragment rendering, since it doesn't make any assumption on the data type that is captured, and it doesn't contain the notion of multiple viewpoints, like in the LDIs. The main reason MFR has been researched in the past is due to its very interesting benefits. First, by exploiting information from hidden layers, you are able to simulate various effects that were not possible before. And examples, for example, include transparency, global illumination, collision detection, CSG, and others. Second, it is based on the rasterization pipeline, and therefore it shares its benefits as well. most importantly is that it's ideal for techniques suitable for real-time rendering and dynamic content. Of course, this is also a disadvantage since it works mainly on sample geometric data, and therefore it results in most cases in approximate solutions. However, these limitations in the last few years can be lifted by using hybrid rendering techniques or more advanced implementations, like combining MFR with ray tracing or voxelization approaches. And finally, it is typically more expensive to evaluate compared to methods that operate on a single layer of information. Now we will make an introduction to the fundamentals of MFR. And in this part, we start with a brief introduction to the rasterization process and the problem of visibility determination. Doing this will form the ground to formalize MFR and introduce a conceptual pipeline that essentially augments rasterization beyond the traditional hidden surface elimination. In its simplest form, a rasterization process receives as input a mathematical description of geometric shapes, and the output is the raster or a rectangular grid of color pixels. And in this process, actually primitives are projected to the image plane, sampled usually at a fixed spatial rate, and in the end they generate a set of fragments at a specific pixel location. What is important to remember here is that the fragment generation stage is executed in parallel. So this essentially means that the fragments are generated in an unsorted order. And what this actually means and requires is that we need to employ a visibility determination algorithm in order to produce a correct image. The most popular and widely used algorithm for primary visibility determination is the Z-buffer, which is efficiently implemented in commodity graphics hardware. And after processing all fragments, the Z-buffer actually stores the nearest visible fragment with respect to the camera location. In other words, and what is important for us is that it stores a single layer of information. Therefore, it has been widely used and is an excellent choice for a vast number of real-time techniques that require access to direct visibility information. However, applications that require samples for hidden, either occluded or back-faced surfaces cannot be properly implemented by relying only on the depth buffer. With this information in mind, we can proceed to define and generalize this problem as part of multifragment rendering, which is actually responsible for processing, storing, and operating on multiple per pixel fragments. In that sense, primary visibility determination is a subset of MFR, which means that it processes multiple per pixel fragments, but it stores and operates on the closest one, while the MFR pipeline operates and stores an arbitrary number of fragments. So at a conceptual level, the MFR pipeline is responsible for generating and storing and processing and evaluating information from all incoming fragments. And this pipeline is comprised of three main steps. First is construction. Then this is followed by one or more set of operations applied on the fragment sets, and finally image composition, which composes the final image. And all these operations are actually defined by the context of the particular operation in mind. The construction step is responsible for generating and storing multiple per pixel fragments through a traditional rasterization procedure that is repeated according to a fixed number of iterations. Each iteration is executed in one or more geometry rendering passes, and in every geometry pass the outcome is that a fragment subset associated with a specific pixel is selected, stored, and eventually sorted. What is important to remember here is that even though storing and sorting are two fundamental building blocks of the construction step, the sorting stage can be performed either explicitly or implicitly. And also with respect to implementation, it can be applied either as a post-processing step or as an online algorithm, which means that fragments are sorted as they arrive. After construction has taken place, the next step performs one or more operations on the ordered fragment data structure. The most critical operation here is fragment data traversal, followed by other optional ones such as map mapping, compression, and others. The final part is the image composition, which is where the final image is composed. And what actually does it accesses and exploits the fragment information stored in the data structure so far in order to compose the final output. For example, transparency merges the sorted fragment list by blending in order to produce the final output. Now let's go into more detail to each part of the pipeline. The first stage is construction, and without loss of generality, the MFR buffer construction techniques can be classified according to the maximum number of per pixel fragments captured in one iteration for each method. So we actually have three broad categories here: depth billing, K-buffer, and A-buffer methods. First of all, depth billing methods process all fragment information through an iterative pipeline using few and bounded memory resources. And depending on the technique used, each iteration uses one geometry pass and is able to extract a limited number of fragments, like one or two, with guaranteed depth order, which actually means that sorting actually happens implicitly in these methods. On the other side of the spectrum, a buffer methods aim at capturing all fragments in a single iteration step, so this is not an iterative method. And typically fragments are stored into GPU accelerated data structures during a single geometry rendering pass that is followed by a post-sorting operation that reorders them according to their depth. Finally, K-buffer approaches offer a middle ground between the traditional depth billing and the more advanced A-buffer approaches. In general, K-buffer methods are capable of capturing the K-best fragments in each iteration, and in most typical scenarios, by K-best we usually mean K-nearest fragments with respect to the viewer. Compared to depth billing, using a K-buffer, usually we require fewer iterations, and that's because we can capture a larger subset of fragments in each iteration. However, we are also required to manually sort the fragments ourselves. Probably the most well-known iterative MFR technique is the front-to-back depth billing. This method works by rendering the geometry multiple times and extracting a single fragment layer per iteration in ascending depth order. Specifically, the algorithm starts by rendering the scene as usual and writes into the depth buffer the closest fragment to the camera. Then it proceeds in an iterative fashion where in each iteration the next closest fragment to the camera is recorded. And finally, the process stops when the maximum number of iterations as set by the user is reached, or if no more fragments are generated. Next, the dual depth billing method is able to capture bidirectionally both the nearest and furthest fragments with respect to the camera in each iteration. Therefore, is able to drop the complexity in half. And the core idea here is to apply the previous depth billing method for front to back in the front to back and back to front directions at the same time. The dual depth billing method was later augmented to extract two fragments per depth bin in each iteration. Therefore, it was able to reduce even further the necessary iteration. And each depth bin here corresponds to a uniformly divided interval of the pixel depth range. In general, depth billing methods are susceptible to Z-finding artifacts, as in the Z-buffer, and this happens when two or more generated fragments in the same pixel have similar depth values. And the authors here proposed a number of solutions that mitigate the depth coplanarity issues that were present in previous depth billing methods. In general, the main advantages of depth billing methods is that they have low and bounded memory requirements, They do not need post sorting, and they support older hardware, offering increased portability and ease of implementation in diverse architectures. On the downside is that they can become very computationally expensive due to the overhead imposed on the geometry processing stage for a large number of iteration steps. Moreover, they are mainly suitable for applications that rely on sequential fragment processing, like transparency. Nevertheless, depth filling algorithms are still widely used nowadays, and they're the optimal choice when sufficient visual quality can be achieved by processing only a small number of fragments. Now let's move to the A buffer. Conceptually, the A buffer construction requires two stages. First, a store stage, which is responsible to capture all fragments in one iteration in the form of an unsorted sequence. And second, a sorting stage, where fragments are sorted according to their depth. The buffer can be typically implemented either as a linked list, or as a fixed size array, or a variable size array. These methods will be discussed next, and this will be followed by more general discussion on A buffer sorting. Historically, the first MFR approach was the linked list A buffer. The main idea here was to store the generated fragments, all of them, in linked lists, instead of keeping only the closest visible fragment. The GPU implementation actually requires two buffers that operate on per pixel linked lists. One is the head buffer that contains the head pointers to each list, and second, a node buffer that stores their data and connectivity information. What is important to remember here is that since the lists are created in parallel, the use of atomic operations are applied to ensure the correct modification of the shared data. However, linked lists suffer from two limitations. First, they require a memory preallocation step in order to reserve the memory space needed, since dynamic memory allocation for new nodes is not possible within a shader. This is decided manually, usually, and can result either in wasted space or memory overflow, which is, usually manifests as flickering. Second, the non-contiguous allocation patterns of the linked lists can result in memory indirections and cache misses, and consequently they can cause performance degradation. Since the first GPU implementation, the research community has focused on ways to alleviate the aforementioned limitation. These include improved cache coherency by memory paging, bidirectional traversal using double linked lists, and the exploitation of tiling mechanisms to mitigate memory overflow issues. A simple approach is the fixed array buffer. These techniques allow the storage of all fragments in fixed size per pixel arrays. These methods are usually implemented with the assistance of an additional count buffer. Compared to a linked list, there's no need to maintain node pointers, and fragments are stored in contiguous memory locations. This has a direct consequence in the cache coherence and therefore in the speed. On the downside, these methods suffer from huge allocated memory space being wasted, and this because in typical scenarios scenes have uneven fragment distribution, while these methods pre-allocate a fixed size array for all pixels. Finally, variable size arrays are an attempt to combine the advantages of fixed size arrays and linked list structures. And what this means is that they actually aim to store information in contiguous regions without over allocating memory space. And typically, um, these methods require two additional passes before the storing stage. First, one geometry pass to count the exact number of fragments needed for the allocation, and second, a screen space pass which counts the per pixel head pointers through a prefix sum operation, and finally this is followed by the actual geometry pass which fills the memory space using the information stored in the head buffer. On the downside, these methods are usually more complex to implement and can be less efficient on scenes with high geometric complexity, and this is due to the extra geometry pass that is required for counting the fragments. To sum up, the various iBuffer alternatives that exist, they cover a broad range of features, and therefore there is no optimal solution for all scenarios, but rather a more suitable match for each application's requirements. Fixed size arrays are the simplest to implement and most efficient in practice, but can waste a significant amount of memory that remains unused. So they should be employed on scenes with uniform fragment distribution or applications where memory is not an actual issue. Traditional linked lists can accommodate more complex environments at the same memory budget by trading uh, tighter memory allocation with less efficient cache utilization. Finally, variable size arrays are the most elegant and are preferred for applications with stricter memory budget. However, due to the extra geometry pass required, they're not the optimal choice for environments with high geometric complexity. So now let's talk a bit about the sorting states. After all fragments have been stored to the A buffer, they're sorted by depth in a subsequent screen space pass, as we discussed earlier. This process in general is divided into four main consecutive steps. First, the depth values of the capture fragments are fetched from the global memory. Then the data is stored onto a per pixel local structure, like a local array. Third, the local data is sorted based on the depth. And finally, the sorted data is stored back into the global memory. In typical environments, the fragment generation is not regular, so the sorting process can actually result in performance bottlenecks. And this is due to several reasons. One is due to poor coalescing of global memory, something that is mostly present in lists during the read and save stages. Second, there's a bad local memory utilization during the store stage, since neighboring threads contain different lengths of fragment lists. And finally, due to thread divergence during the sorting process for the same reasons as before. So now let's discuss what the research community has proposed in order to mitigate those issues. With respect to bad local memory utilization, there's been two novel approaches proposed to improve the management of local GPU caches. The first approach works by performing different screen space passes, where in each screen space pass a list of different fragment length is sorted. The second idea partitions the depth sorting into batches and iteratively sorts the larger list using a smaller amount of local memory. To reduce the thread divergence, researchers proposed altering the sorting algorithm on a per pixel level based on the list length, or have exploited other sorting approaches like bin sort or register based block sort. In practice, however, choosing the appropriate sorting mechanism is application dependent, and more specifically, it's related to the generated fragment distribution. So, modern applications can employ a combination of the described methods, and a typical one is using pre-allocated length arrays with a combination of register-based block sorting. The last approach we will discuss is the K-buffer. This data structure is able to reduce the computational cost and memory consumption by capturing the K-best fragments in each iteration, and usually these are the ones that are closest to the camera. In practical scenarios, however, only a specific portion of the fragment pool is enough for plausible results. So, for example, in the case of transparency, one iteration is usually enough for producing the correct output. So, in general, the algorithmic process of any k-buffer variant is as follows. For each incoming fragment, we initially fetch the capture elements of the k-buffer for each pixel from the global memory, and we copy them to the local array. If the fragment is deemed to be not important compared to the existing ones, it can be safely discarded. Otherwise, the current fragment subset is updated accordingly in the local array, and then it's written back to the global memory. There are two issues that should be discussed here. The original algorithm suffered more or less from disturbing flickering artifacts that were caused by read, modify, write hazards, and these were happening when the generated fragments were inserted in arbitrary depth order. A second important issue is that the number of K is fixed and predefined for all pixels, and this can lead to various issues. For example, using a small K can result in view-dependent artifacts, since more than K fragments may be required for a particular viewpoint. On the other hand, using a large value of K can result in wasted memory allocation and consequently reduced performance. To eliminate any race conditions that happen when fragments belong to the same pixel, two major categories of methods have been proposed. The first is multi-depth testing approaches that guarantee correct depth order results by capturing and sorting fragments on the fly using atomic operations. And the second category are pixel synchronization solutions that utilize either hardware or software spin lock mechanisms to ensure atomicity. To mitigate problems that arise from using a fixed K, the K value can be either dynamically adjusted by performing a depth histogram analysis first, or it can be set differently on a per pixel level according to, for example, important space criteria such as foveated or BSDF based importance, as proposed in the variable K buffer. In practice, however, only fixed solutions have been employed. For example, for hair rendering in AMD's TrueSFX. Dynamic solutions, however, are more elegant and could eventually be more useful for problems like in selective rendering or augmented and virtual reality, but further research is required to address performance issues and maybe choosing more advanced selection criteria. So now we'll start discussing some of the most common operations. The most widely used ones are probably the sequential depth traversal, as well as the screen and pixel space traversal. The last two are usually what is referred to as image space ray tracing. Other operations have also been employed in the literature that essentially alter the data structure either through connectivity, composition, or compression operations. The unidirectional depth traversal is by far the most common operation. Here, the per pixel fragment elements are accessed in sequential front to back or back to front order. Due to its very simplistic nature, it is used pretty much everywhere. However, object independent transparency and CG are the most typical examples of this operation. The ideal data structure for this operation are the array-based ones, and this is because this operation requires or works more effectively with contiguous element access, better cache locality, and support of binary sets. Image space traversal is a critical part of image space ray tracing. Essentially, what it involves is the access of fragment lists at different and arbitrary pixel locations, allowing the propagation of rays within a visual environment. This has been widely used in single layer techniques originally, with the most simple and efficient one being the object space linear array merging. What actually happens here is that each ray is sampled at fixed object space locations and tested against the depth values for intersections. This approach performs very efficiently, however, it suffers from under and oversampling issues. This can actually be remedied by iterating in single pixel increments instead. For example, by employing a 2D digital differential analyzer. This method is able to capture both contact details and distant geometry. However, moving along every pixel can become really fast, really prohibitive for real-time applications. To capture the entire image space domain effectively, ray traversal can be also performed hierarchically, therefore reducing the complexity to logarithmic. This typically has been accomplished using different ways. For example, by following a height field based approach, or by mapping the depth boundaries, or even through merging and clustering similar neighboring fragments. Once we visit a candidate pixel in image space, then we need to identify a potential intersection between the ray and the pixel, and this actually is performed by testing the image projected ray against all fragment samples that are assigned to that pixel. There are two major approaches here. First, approximate solutions that work by comparing the array's depth extents against the depth sample's depth extents in order to identify a hit. And second, analytic approaches that operate on primitive indices instead. And these primitive indices are usually captured in per pixel linked lists. And these methods can offer accurate ray primitive intersection tests. Another interesting operation that can essentially alter the MFR data structure is the fragment neighborhood discovery. Typically, this is employed to enhance model visualization applications, for example, for spatially aware transparency. Apart from sampling and filtering operations at the fragment level, though, computing the connectivity between fragments of neighboring pixels also allows for the estimation of thickened boundary representations of the surface geometry. And this is useful, for example, for more robust collision detection applications. Multifragment composition is a recently used operation for the generation of complex production images from multiple sources. This type of operation actually enables some interesting additional capabilities. That, for example, one can efficiently insert additional information from one buffer to another without requiring the entire frame to be re-rendered. Finally, a number of offline and online techniques for compression have been introduced, in which compressed data sets are computed in a way that do not significantly affect the visual quality of the target applications. For example, applications like these include object independent transparency, shadows, and anti-aliasing. One idea here is to perform compression on a per layer fashion, like this, using image coding schemes, where color and depth information for each layer are computed separately. Another idea is to perform a compression on a per pixel basis, where streaming algorithms have been used to perform, for example, on the fly rejection of or merging of incoming fragments. In this last section, we identify some key application domains of MFR. If you recall, an application is actually a complete MFR pipeline. It essentially uses the information that has been stored inside an MFR data structure, and along with the set of operations that we already described, it produces the final image. So here we briefly present some of the most important applications in this domain, and provide the recommendations for choosing an appropriate method for each problem. Please note that there's a large amount of research here, so for more details, please refer to the paper. The majority of research ideas in the MFR domain has started by the demand for efficient and correct simulation of transparent surfaces, including hair rendering and CAD visualization. The core idea here is to traverse the sorted fragment list in a back-to-front manner and apply the overcomposition operator on the fragments color data in order to compute the final color of the transparent surfaces. In this category, actually, all types of MFR data structures have been researched and extensively. However, we recommend that using a K-buffer is the optimal choice, since the transmittance along the depth axis rapidly attenuates and can be compactly represented using only a few layers. Another important application that the research community has focused on is shadow rendering. For example, storing multiple levels of occluders on compact buffer representations as they are rendered from the light source can enable various effects. For example, soft shadows with varying penumbra filters, or the simulation of volumetric media, or a rendering of semi-transparent surfaces. Alternatively, you can store light receivers in A buffer linked lists, and doing this, it has been shown to produce alias-free shadows for point lights through the concept of irregular Z buffers. In general, shadow generation can benefit from compact buffers, since the stored information may correspond to either an approximate transmittance function or a partial occlusion estimate. Traditional single-layer GI techniques are fast, but suffer greatly from visual instabilities due to the missing geometric information inside and outside the viewing frustum. With MF4, it has been shown that image space GI can be greatly improved by combining the multi-layer information that is stored in the per pixel data structures with the image space ray tracing operations that were discussed previously. Here, the choice of which MFR buffer to use really depends on the application type. For example, for low frequency environments, shallow buffers are usually enough for visually convincing results. However, for more accurate results, or scenes with highly directional scattering events, it is best to use either an A buffer with analytic primitive intersection tests, or go to a hybrid solution where you can combine, for example, a K buffer with an object space acceleration data structure. The flexibility offered by storing multiple layers of information has also driven the community towards improving distribution effects and filtering techniques. For example, the traditional problem of anti-aliasing has been one of the main goals of even the very first A buffer in 1984, where the final color was computed by merging fragment lists with their coverage masks. This work was also the driving factor for other anti-aliasing hardware architectures that were proposed later on. For depth of field effects, critical information of out-of-focus objects resides on the hidden fragment layers, so MFR approaches are actually good candidates to produce highly convincing results. Finally, denoising techniques have also used contribution from objects at different depth locations, thus providing an advanced framework towards denoising deep composition workflows in production rendering. From any of the aforementioned applications that are mentioned here, we believe that retaining a low count fixed size fragment list is generally sufficient to produce convincing results. Another diverse set of applications we have identified is constructive solid geometry and scientific visualization. Without loss of generality, these categories need computationally expensive operations, either for the modification of existing objects or for the visualization of large datasets. Since MFR data structures provide an efficient way to store and traverse lists of per pixel fragments, they have been used for the classification of surfaces into interior or exterior, and for the combination of different volumetric and solid models. The potentially large number of layers in scientific and CAD visualization tasks, we believe that it mandates the use of an A buffer. So, for the visualization of massive data sets, however, this could be further improved by using techniques that compress the farthest fragments, as their contribution to the final image is most likely negligible. Now let's move to the last part of the presentation, where we present and briefly discuss a number of open and challenging issues that we believe remain partially covered or even unresolved in the literature. First, while exploiting spatio-temporal coherence has been shown to greatly improve single-layer techniques, we have observed that similar methodologies have not really been applied to the MFR domain. Therefore, a very promising direction here would be to exploit reprojection and reuse fragment data from previous frames in order to achieve deep buffer construction at an even lower cost. Moreover, MFR strategies have not been thoroughly investigated in efficient stereoscopic rendering. Here, elegant approaches could exploit information of MFR in order to reproject fragments for the different cameras with a greater success ratio and smaller error compared, for example, to single layer techniques. Another problem is the massive amount of information that has to be processed in every frame and can quickly stretch the MFR solutions to their limits. These problems have become more evident in the recent years, where applications have become very demanding in terms of both content complexity and photorealism. Even though various elegant strategies have been proposed to improve rendering on either per layer or per pixel or even per application basis. We haven't seen something that has a solution, an elegant solution on a holistic fashion. Therefore, this is a direction that we believe that it could be explored further. We know that the process of rasterization imposes some very severe limitations in the graphics pipeline, since what actually happens is that a continuous primitive is represented by discretized samples at specific locations in the image plane. This actually results in three main sources of spatial aliasing. First, for example, polygon edges and oblique geometry are sparsely sampled, while geometry that is either parallel to the view direction or residing outside the view frustum is skipped entirely. So, even though various approaches have been investigated, such as conservative rasterization and others, view dependencies are still an open problem in screen space techniques. On the other hand, the recent launch of NVIDIA RTX platform has enabled hardware accelerated ray tracing computations, thus enabling a new era of hybrid ray tracing and rasterization techniques. So here we believe that we should continue harnessing this trend to devise smart hybrid MFR ray tracing methods. With respect to device platforms, the range of devices that can offer highly immersive experiences and high quality graphics has thankfully been expanded over the last few years. Some of these devices, however, like various mobile platforms or virtual and augmented reality devices, are highly constrained. So we believe that it would be very interesting to see research problems that may arise when MFR approaches are applied in various other architectures with, for example, a low latency bandwidth or a very high memory constraints. Even though the rapid evolution of GPUs has greatly impacted the multi-fragment processing capabilities in more than one ways, for example, including atomic operations, dynamic memory allocation rights, and pixel synchronization, we believe that novel specialized modifications to the current hardware pipeline are essentially required to enable full hardware accelerated support of K buffer or A buffer solutions on future GPUs. For example, here some ideas may include hardware friendly MFR implementations or for example, expanding variable rate shading to the depth domain. Lastly, a very interesting observation is that the driving force on MFR research has been the improvement on the quality and performance of transparency applications. However, the number of graphics applications that progressively rely on MFR solutions have increased, like in ray tracing and big data visualization applications. Therefore, it would be really interesting to see the MFR domain covered to a larger application extent and see what further opportunities for research will be presented. Finally, we believe that there's a strong need for a generalized MFR framework for prototyping and for providing comprehensive benchmarks and validations for the complete MFR spectrum based on realistic and practical data scenarios. So, to finalize with this survey presentation, we provided an overview of an insight into the extensive yet active research on multi-fragment rendering. We presented the MFR pipeline. We discussed various construction strategies and core image operation categories and their mapping to the respective applications. We also described features and trade-offs for each class of techniques and provided some practical recommendation for choosing an appropriate method for each application. Finally, we offered a fruitful context for discussion by outlining some existing problems and challenges. I would like to close by saying that this research has been co-financed by Greece and the European Union, and that we are grateful to all the authors for granting permission to use their images in the presentation and in the paper, as well as to the anonymous reviewers for their constructive comments. More details related to MFR can be found at our research group and our corresponding GitHub page. And my colleagues and me are here, and we would be happy to answer any of your questions. Thank you for listening to the presentation.
So we're back live, and thanks everybody for watching. So we have one question from Michael. Do you think that MFR can be applied to deferred rendering, or it is limited to forward rendering because of its memory usage? Apparently, MFR has been applied to deferred rendering, and all the information is included to the star. I think there are two works describing how it's gonna be, how it's applied. And yeah. So second question from Marco. Are you aware of application using streaming of multi-fragment data? That's a difficult one. In essence, for remote rendering, I guess we can say that there is some partial information being transferred from clients to server side for rendering, but it's not something that has been extensively exploited so far. So yeah, that's a very nice future direction, because it's all can be combined how we can compress this information in order to be easily encoded and decoded from one side to another. So I think that's all. That's all the questions. Thank you very much again, and also we are. If you have any other questions, we are will be available through the Discord channel in order to answer any other questions there. Thank you again.